This is the third video for the probability and statistics unit, and we are looking at the addition rule in this set of notes, which I think you will be finding is pretty straightforward. So we're going to start off reviewing, just making sure we know what's going on. So we have a table here about surveying on students eating breakfast before school. So in this table, what is the probability of selecting a student who is female? We have 331 students in all, and of those 331 students, we can see that 199 are female, which gives us 0.6012. What's the probability of selecting a student who ate breakfast? So that's the students who said yes in this table. We have 191 students that said yes out of 331. So 0.5770. What is the probability a selected student is a female, given they ate breakfast? So what do we know to be true about this student? It's given they said yes. We're trying to find which of those are female. So this time, we're only looking out of the students who said yes. So that's 191. And out of those 191, 125 are female. Type that into your calculator and you can get the decimal. What's the probability a randomly selected student ate breakfast given the student is female? This time, our denominator will change. We are given it's a female. So we know that there are 199 females in all. And out of those 199 females, how many said yes to eating breakfast? 125 of them. So we end up getting 0.6281. What is the probability a randomly selected student is female and ate breakfast? So this time we're looking for the probability of female and yes. We're still talking about out of everyone. What's the probability out of everyone? The person we selected is female and ate breakfast. Go to your table. There are 125. 0.3776. So, are eating breakfast and being female independent events? So remember, if they're independent events, the probability of one does not affect the probability of the other. So here's what that would mean. The probability of eating breakfast giving female would equal the probability of someone saying they eat breakfast. In other words, the fact that you're given female does not change the probability of saying yes. And we're checking this, so I'm going to put a question mark over it. We actually found these probabilities earlier in the problem. The probability of being a female, given female, and saying yes to breakfast is 0.6281. The probability out of everyone says yes is 0.577. These are not equal, so they are dependent. Remember, if they're independent, in the subgroup of females, the probability that in that subgroup you get a yes would be the same as the probability of the whole saying yes, and that would be independent. So we're using the same table. Moving on. What is the probability a randomly selected student ate breakfast or is female? So yes or female. So we need to figure out who all fits this selection. So how many students do we have that said yes to breakfast? We had 191 out of 125. We also, I'm going to write this as one fraction. That one didn't make any sense. Let me back up. Okay, so we have the probability of saying yes or female. So again, we are talking about out of everyone, so our denominator will be 331. How many ate breakfast? So go to your table. There are 191 students who ate breakfast. Or female, we have 199 that are female. The problem is, if I look at my table, I'm looking at the yes column and the female column. I have a group that has been double counted. So I can't double count those. I need to turn around and subtract 125, that double counted group. So I end up with 265 over 331. What's the probability a randomly selected student did not eat breakfast? So I'm going up to my table. That would just be the no column. There are 140 students out of 331 that did not eat breakfast. What's the probability the student is male? We have 132 males out of all of our students. What is the probability a randomly selected student is male and did not eat breakfast? So go to your table. How many males did not eat breakfast? There are 66 out of all of our students. What's the probability that a randomly selected student either did not eat breakfast or is male? So we have to figure out what our possibilities are. So how many students did not eat breakfast? 140. How many are male? 132. The problem is we have a group that we have counted twice. So we have 66 males who said no. We have counted those twice. So we need to subtract that from our total that would fit our requirements of not eating breakfast or male. And yes, we're dividing that still by 331. So we get 0.206 over 331. Type that in your calculator, 0.6224. So what we have actually looked at here is called the addition rule. And the addition rule is dealing with an or statement. And so the probability of A or B is the probability of A occurring plus the probability of B occurring, and then you subtract your double count, the probability of A and B occurring. Now there are times that they do not overlap, and so you don't have to worry about subtracting anything if you're not double counting. We'll talk more about that. You can also represent an or statement with a union symbol, so you could write that as the probability of A union B. So find the probability. Let's look at example 3. You randomly select a card from a standard deck. Find the probability it's a jack or an ace. So this is an or statement, so we're going to use the equation we came up with above. Again, this is pretty intuitive. We have 4 jacks. We have 4 aces. Now notice it says subtract P, the probability of event A and B. We have no cards that are jack and aces, so we don't have to worry about subtracting anything here. So there are 8 cards out of the 52 that meet our requirements. Find the probability of rolling a number less than 3 or an even number. So how many numbers are less than 3 on a die? 2. 1 and 2. Plus the probability of an even number. There are 3 outcomes there. 2, 4, and 6. Have we double counted any of those? Yep, we have. 2, the number 2. So we've double counted one event. We end up with 4 out of 6 here. So that's the use of the addition rule. So we've got another table here. I'm addressing the same thing. This table involves blood types. So we can have O, A, B, AB, and then each of those can be positive or negative. We're selecting a donor at random. Find the probability that the donor has type O or type B blood. So there are, first let me go find my totals here. I have those. So in all, we have 409. So I have those for you so we can quickly add those together. So find the donor. We ran the probability of selecting a donor that has type O or B blood. We have 184 type O. We have 45 type B. Do we have to subtract? Are there any we double counted? Nope. We don't have any that we double counted out of the 409, and so we end up getting 229 over 409. The donor has O negative blood. Go to your table. There's only one group that has O negative blood, so 28 out of 409. And you can type that in your calculator. Find the probability of having either type O blood or negative. So how many type O bloods do we have? We have 184. How many negatives do we have? 65. Will we need to subtract any? We have this group that has O and negative that we need to subtract, so we need to subtract 68 or 28 from our total. So we end up getting 221 over 409.5403. The donor has type AB blood given the blood was negative. So what do we know to be true about this person? We know that they have negative blood. So how many have negative blood? Only 65. Of those 65, how many have AB blood? If you look in your table, you see that there are only 4. The probability of having AB blood. Now notice that's out of everybody, so we're doing out of 409. Well, how many AB bloods do we have out of 409? 16. That gives us 0.0391. Then we're asked the question, is type A blood independent from having negative blood? Well, remember what that means is the probability of AB given negative, if they're independent, would be the same as just having AB. And what that means is the fact of whether your blood is positive or negative does not impact the fact that you have AB blood. If these are equal, they are independent. The probability of the negative doesn't affect anything. However, when we go back and look at the previous problem, we've actually figured this out. 0.0615, does that equal 0.0391? No, they do not equal, therefore these are dependent. So our last page of notes here is actually something that you've worked on before. You can read the problems up above. I'm going to go straight to the examples. We've already discussed probability or an experiment. Remember that an experiment applies a treatment. So if we need to decide which would be which. To find out whether car accidents are more likely on rainy days, a researcher records the weather conditions and during 50 randomly selected accidents for the year. A researcher records the weather conditions during 50 randomly selected accidents for the year. Let me read that appropriately. So did the researcher apply a treatment? No, he just observed. So this is an observational study. A researcher wants to know if soil additive will make ferns grow more quickly. He grows one specimen in treated soil and the other one in untreated soil. So was a treatment applied? Yes. You applied treatments. You treated soil and untreated soil. So therefore, this is an experiment. A scientist measures the height of 20 birds' nests and counts the number of eggs to see if there's a relationship. Was there a treatment applied? No. So this is an observational study. And this is the end of video